Hi, my name is Aaron Khan, and today I'm going to be presenting my research titled A Bridge Between Innovation and the Environment, Reinventing American Bridge Design for Sustainability Through Topology Optimization and Adaptive Manufacturing. This project focuses on how we can rethink traditional American bridge design to make structures that are not only stronger and more efficient, but also significantly more sustainable. I'll be discussing how topology optimization combined with adaptive manufacturing can reduce material use, lower carbon emissions, and improve structural performance in truss bridges. For some background, truss bridges have long been a reliable and efficient solution for U.S. infrastructure. They are bridges comprised of triangular elements which rely on axial strength of the members to support stable structures. As many bridges across the country continue to age and deteriorate, there's an urgent need for redesigning bridges that use materials more efficiently while maintaining safety and performance. Traditionally, truss design has relied on classical methods such as the Mitchell truss, utilizing theoretically optimal layouts that are often impractical under real-world constraints like complex loading, supports, and fabrication limits. Topology optimization has emerged in recent times as a powerful alternative aided by computers, allowing engineers to determine where materials actually needed to carry loads, maximizing stiffness and stability under realistic conditions. When this optimization process is paired with adaptive manufacturing and 3D printing, it becomes possible to fabricate previously impractical geometries while reducing material use, embodied carbon, and overall environmental impact in more complex structures. As you can see in figures 1, 2, and 3, which are completely original bridge designs made by methods of optimization, which were then adaptively manufactured, from you can see maximized efficiency in the hybridization of the two methods, which shows the feasibility of this process. In this research, topology optimization is used to determine the most efficient material distribution within a truss structure. The process begins by defining a design domain along with the expected loads and supports, and then optimizing the structure to minimize weight while maintaining stiffness and strength. As you can see in figure 4, that design domain is previewed with nodes and support and loads that tell a code where can material be placed and where does the material have to support. Several advanced optimization approaches were explored for my study, including the ground structure method, solid isotropic material with penalization-based density optimization, and evolutionary algorithms. These methods allow optimal loads paths to naturally emerge, producing lightweight yet high-strength truss designs which can outperform traditional size or shape optimization techniques. By combining these optimization results with adaptive manufacturing and 3D printing, the optimization designs can be directly fabricated. This reduces construction time and material waste while enabling fabrication aware geometries that would be extremely difficult or expensive to manufacture using conventional methods. What this process ended up as was a full overhaul of existing designs to maintain loading constraints while optimizing structure and increasing performance for a longer service life. It begins with the existing constraints of a bridge and put it into an optimization code. This specific code was from the Technical University of Denmark, which focused on the SIMP, solid isotropic material with penalization method. It was originally meant for optimizing cantilever trusses, but I remodeled the code and modified it for application on bridge design. Once done, these dimensions and material allotments of any bridge can be entered in a MATLAB prompt for the code to create a new structure. This process was the beginning of this process was applied to a case study in the Trinity Railroad Bridge in Dallas, Texas. By obtaining dimensions and loading constraints via information online, the bridge, which is pictured in figure 5, which was built 100 to 150 years ago, and optimization, once done, could improve rail transport in the region if revitalized. So that's why once the dimensions were modeled, as you can see in Figure 6, the code had to be modified once more for the loading constraints, and then began to experiment with different design and material allotments in the code to create an optimized structure that maximized stiffness and minimized material usage. The optimization results revealed a clear trade-off between these two things, stiffness and material use. By varying the volume fraction, you can see a reduction in overall weight when lowered, but this also led to increased deformation under load, while higher volume fractions improve stiffness at the cost of additional material and consequently a higher embodied carbon, which would reduce environmental which would increase environmental impact and reduce efficiency. Among the dimensions tested for the Trinity Bridge, the 0.35 or 35% volume fraction design stood out as the most effective balance. It achieved nearly the same stiffness as the zero point 0.4 material allotment case, which while also using 12% less material and maintaining a more practical structural height for bridge applications, about 45 feet. In Figure 7, we can see a bridge with a large height of 60 and a large amount of material usage for a baseline stiffness. Figure 8 shows a shorter version, a 30-foot bridge with a steep decrease in stiffness due to the code merging members. This merging occurred because the code had to compensate for a lower material usage, and by hybridizing these load points, there's a lower stiffness because of less support. So as you can see in Figure 9, I determined this Goldilocks area of material allotment and height. Figure 9 is the final optimization, which showed high stiffness compared to the 60-foot bridge in a comparable amount and had a very similar material usage to the 30-foot bridge. And the final thing was that the 45-foot is a very typical, average, and practical railway bridge height. The next step in the full revitalization process is by taking the optimization and applying a computational analysis of this MATLAB design in MassStan 2, which is an analytical software that can simulate bridge performance. When compared directly to a traditional truss design under the same simulated load conditions, the Goldilocks optimized truss consistently outperformed the conventional existing structure of the Trinity Railroad Bridge. Specifically, the optimized bridge design exhibited lower mid-span deflection, indicating greater stiffness and structural efficiency. Figure 10 shows the perfect optimized truss design. And as you can see, there is some deflection under the magnified load, but when compared to the existing Trinity Railroad Bridge design, the existing design shows deflection under the same load in a greater quantity. These computational results confirm that topology optimization is not just a theoretical improvement, but a practical tool for enhancing stiffness performance while supporting material sustainability goals in bridge design for material reduction. The third step in the optimization process is to validate these computational results. Small-scale physical testing was done by using 3D printed truss models of the optimized bridge and the traditional bridge. The optimized design was modeled from the MATLAB design and exported into Microsoft 3D Builder to create a 3D model that could be 3D printed as a physical model. Now, under 100-pound loading conditions shown in Figure 13 and 14, the optimized truss did show lower midspan deflection as predicted in the computational model. The optimized truss showed 0.047 inches deflection as compared to the 0.063 inches that the traditional design deflected. These experimental results validate the computational analysis and the traditional and the optimization. This demonstrates a strong agreement between the optimization models and real world performance, even with material limitations and printing imperfections in the 3D printer itself. Now, these imperfections can be eliminated in larger scale creation because more precision 3D printers are employed for materials like steel and concrete. Both structures in the physical testing remained within the elastic behavior, with no visible damage occurring after load was taken off. This supports the reliability of 3D printing as an adaptive manufacturing process for prototyping and full scale manufacturing, while also emphasizing the need for future large scale testing in order to maintain this result. From a sustainability standpoint, however, topology optimization resulted in a 16.3% reduction in material use. This translates directly into a significant decrease in embodied carbon and a global warming potential decrease for both steel and concrete bridge designs. In the Steel Trinity Bridge case study, the optimization process reduced global warming by 22,249 kilograms of carbon dioxide, which highlights how even modest material savings of very small amounts can lead to substantial environmental benefits at full bridge scale. These results confirm that structural optimization lowers emission regardless of material choice. And when combined with adaptive manufacturing and informed material selection, it offers a powerful strategy for reducing the carbon footprint of future revitalization projects in bridge infrastructure. Because as you can see in tables 1 and 2, the carbon dioxide emissions decreased sharply for optimized designs in both traditional and optimized designs. There was a steep decrease in carbon dioxide for both concrete and steel as a material. Steel and concrete are the main used materials in bridge design, which highlights the application variety of this process. So in conclusion, this study presents a comprehensive framework that integrates topology optimization with adaptive manufacturing to redesign traditional truss bridges. In 3 steps: topology optimization, computational modeling, and adaptive manufacturing, the approach improves structural performance while significantly reducing material use and environmental impact. As demonstrated through computational modeling and physical testing of the Trinity Bridge case study. The optimized bridge design with a 0.35 volume fraction achieved a effective balance between stiffness and efficiency, using about 12% less material while delivering roughly 20% better structural performance and reducing the global warming potential by over 22,000 kilograms of CO2 equivalent, a 16.3% decrease. However, moving forward, further research is needed to scale up adaptive manufacturing for full-size bridges to develop reliable print construction methods and joint systems, refine embodied carbon data, and integrate life cycle assessment into the full-scale adaptation of truss bridge optimization. This all culminates into a more deeply investigated optimization workflow, which ensures long-term sustainability in revitalization of infrastructure. And that is my study. I will say it was a very interesting topic to explore, and I definitely enjoyed the results that I got. Thank you for watching, and I hope you enjoyed what I discussed, and I hope it makes you wonder about the potential of optimization for infrastructure. Once again, thank you for watching.